Okay, so hey guys, again, it's Sam here. I would like to talk to you about Leetcode Weekly Contest 163, and I just did it today. So out of the 4 problems, I finished the first 3 because you can see like the hard one, like the last problem has a really high score, which means it's really difficult. So yeah, it was in my expectation that I couldn't solve the last one within the time limit, but like I really dug into the last one and I solved it in like 90 minutes, which is pretty good for me, I guess, because like 8 is just really hard for me to solve it on myself, and I'm really glad that I did it. So yeah, so I solved the first 3 problems within 30 minutes, and that placed me about 250th, which is pretty good. Like my goal right now is just to get into top 300 for each competition. Should be fine. Okay, so let's look at the problems then. The first one is pretty straightforward. It's shifting 2D grid. So you're given a 2D array as input and of size m times n, so like m rows and n columns. And an integer k, you need to shift the grid k times. And how exactly do we shift the grid? It's really straightforward. So it's just like shifting this element to there and pushing the 3 down to the next row. So like this, right? After you shift once, the 1, 2 gets placed here because they get pushed to the right by 1 unit. And then the 3 is pushed out. So instead it goes to the next row, right? So the same for the next row and same for the last, except that because 9 gets pushed to the right, but 9 doesn't have anywhere to go down. So it goes to the very top to fill in like the empty position made by the first row. So it's pretty straightforward shift. Like what I did is just like I simulated the shift, and because like basically like the shifting row that I just talked about is basically what those 3 lines tell you. But they also show you like how you can kind of easily implement it, just like I did. So basically what I did is like I said for each row, okay, for each row, if the element is not the last in the row, just shift it to the right a bit. If it is the last in the row, like a 3, I put it to the next row. So the same for this, same for this. And I say like, if I'm on the very last element, then I put it to the top left. And it's the same thing as what I just talked about, the same shift. So yeah, basically like I did a for loop. And temp is like, so temp is like the grid after 1 shift. Like it's newly generated per shift. So in the first, like I shift k times, right? K times in total. And each time like temp represents the next, what the array looks like after the next shift. So it gets updated continuously. And here's what I just, like, this is basically what I just said I did. So if j is for each row, if j is not the last element, just shift it by 1 to the right. And yeah. Then if I is not 0, so this is for the last element in the row. If I is not 0, so if it's not on the 0th row, then like it goes, so like the temp, so this is the temp basically after 1 shift. So this element equals to this one. So this is what this line tells you. And if if I is in the last row, or if I is in the first like 0 row, because like this is temp and it has to this 9 comes from the very bottom right. So if it is 1, temp 0, 0, no, sorry, if it is 0, if I is 0, temp 0, 0 equals to the very right element of the grid. So it gets, it keeps updating, updates k times, and yeah. So then eventually, like in the last iteration, the grid is the correct permutation, like we should return. And because we return a list integer, list integer, we just put the array into the two-dimensional list and then return the result. Yeah, it's pretty straightforward. Let's look at the time. Okay, I wasn't surprised about it because like I think there are more efficient ways to solve this problem, but like because it's easy and like the way to solve it is already given here, so I just like implement it because it's like a competition. It's not like testing how fast your code is. You only have to pass it, so that's basically what I did. The next one, find elements in a contaminated binary tree. Okay, it says it's contaminated, but basically it means that initially all the elements in the binary tree is -1. Every single element is -1, right? This word is useless, but I mean like they do it anyway, so yeah. So it gives you a structure, basic structure of the binary tree, and every element initially was -1, and you want to return something like this. So you want your root to have 0, and you want any like left node to have like this number times 2 plus 1, like this, and you want the right subtree's value, subnode's value to be 2 times the root plus 2, or like here's a better example. So initially you have 0, so its left subnode should be 2 times 0 plus 1, which is 1. Right subnode is 2 times 0 plus 2, which is 2. And then, because we have this structure, now like this, we keep going down, this node, its value is 1. So to its left, the value should be 2 times parent. So 2 times 1 plus 1. This one should be 2 times 1 plus 2, which is 4. So here's basically what it means. So it's just like, yeah. It's basically like a binary tree, or like the usual binary tree indexing, which is pretty straightforward. So it wants you to implement 2 functions. First is like, yeah, I thought like first is the constructor, which is this. It wants you to basically clean the tree. So like turn the tree in, like fill in the nodes with the values they should have according to those 2 rows. Like 2 times the parent plus 1, 2 times the parent plus 2. Like change their value so that they satisfy those 2 rows. And that should be really easy. So like I just wrote a helper like clean, because like you're initially given a tree when you establish when you create an object or find elements, because like you're initially given this structure, right? So the structure is already given to you. You just need to like initialize a tree within your class, and then put this the tree equals to the given tree. But before that, you have to clean the tree, right? So you clean the tree, make it look like this, then set the tree variable in your class to clean the tree. That's what we should do. So I wrote a helper function, clean 0. So like the int num represents like the current node's value. So if we're on here, num should be 2. If we are on this node, the num should be 5. So yeah. And initially, because we want the initial root value to be 0, when we like call the function, we just set the initial num as 0. So the clean function is also pretty straightforward. Like so first, like apparently if root is null, if it's like a empty node, then just do nothing because it's a void function. Just like we have the structure, so we just need to clean it. We don't need to return a new tree. So we just do a void function. And if root is null, means there's nothing we can do, it's empty. But like if it's not empty, then yeah, so yeah, so like we set the root dot val to like the value it should have according to the rules. So initially, for example, we call it as clean root dot 0. And like apparently at this node, it's not an empty node. So we just set the value of the root to 0. Then we recursively call the functions. So we basically like call clean root dot left. So clean the left subtree, and we change the num. So like the value of the node to num times 2 plus 1 in order to satisfy the rule. So for example, in here, the num becomes 0. Sorry, the num becomes 1 here and 2 here. So yeah, and those nodes will change its value to 1 and 2 respectively and keep going down. Yeah, so recursively call those two functions. So you will like traverse through the whole tree. And then after the recursive function is called, the root, like the tree has all its nodes with their corresponding correct values. Then we just like set the variable, class variable root to the given variable root. Okay, the next function we need to implement is find. So return if the target value exists in the recovered binary tree. So it's a little bit tricky, but it's it's okay. I think it's fine. So basically, like, because when you read the given values, this is a really good hint. So they will call the find function at most like 10,000 times, and the target value should be like between 0 and 10 to the 6. So like if you go through all the target from 0 to 10 to the 6, like so like if you basically, it's like if you try to do a linear search of the tree. No, sorry, not a linear search. So if you search through all the nodes to find the target nodes in the tree, it will be like at most, I think there will be at most like, yeah, the number of nodes is between 1 and 10,000. So like the number of nodes will be, so each time the find function will like compute the value of 10 to the 4th nodes, and it will like call find 10 to the 4th time. So it's actually, I think it's actually fine. Shit. Okay, I could have implemented it more easily, but whatever. I did a very efficient solution. So yeah, so in total, if you multiply them up, you will compute like at most 10 to the 8th times, which should pass. Yeah, fuck me. Well, yeah, what I did was much more efficient. Whatever. So basically, I thought in a reverse way. If I have a target, can I find like the particular path it should follow? Because like you see, like each node, each value has different paths, right? Like 3 and 4, they have different paths from the root. So I thought to myself, could I know exactly what the path should be if the node exists? So for example, 11, I should know that it should be right, left, left, right? So here's what I thought. Notice that all the values like on some nodes left, like here. So if we look at 2, right? It's this left subnode's value is 5, which is odd. And look at 5, its left subnode's value is 11. So why is that? It's because this value equals to 2 times 5 plus 1. So 2 times something is even. 2 times something plus 1 has to be odd. So I thought like we can use that trick, right? Like if you have a subnode, if you have a node, its right subnode's value, 2 times this node plus 2 has to be even, and its left subnode's value has to be odd. See, left has to be odd, right has to be even. So what I thought is like I could like see if like this. So if I have a target, if my target is 11, I can see if it's even and odd. If it's odd, it means it has to be it has to be some node's left subnode, right? Because if it's odd, like it goes to the left. So I say, okay, I add I add a pass left. So basically what I did is like, I subtract 1 from 11 and divide by 2. Basically, because like 2, I don't know, even though I don't know what this value might be, I only have the target 11, right? So I don't know what its upper parent node is. But I have a function, so 2 times x, this value has x, 2 times x plus 1 equals to 11. So x equals to 5. So after, like according to the rule, I can calculate what its parent node is, right? Then I keep going up. I have 5. 5 equals to like 2 plus this value, 2 times this value plus 1. So this value is 2. Then I say, okay, so 2 equals to, because 2 is even, so 2 equals to 2 times this value plus 2. So this value is 0. Then I reach my destination, right? So here's what I implemented. I basically like did a while loop. Temp is the target. While temp is not 0, if it's even, then so first I constructed a list. Then I say like if it's like if it goes to right, I just add 1 to the list. So 1 is just like my version of using representing the pass to the right. And if it's odd, so if it's even, I subtract 2 and I divide by 2. If it's odd, it means it's left. So left is 0, right is 1. Yeah. Then I subtract 1 from temp, divided by 2. And then I get the complete pass. But like this pass is in reverse order. So here, for example, I would get left, left, right. So I have to, when I go from the top, I have to search in reverse order. So I go right, left, left. So yeah, then I also wrote a helper function to find. F returns a Boolean. Basically, it finds whether target exists in the tree. So if R equals to null, I will return false, right? Because it reached an empty node, but we haven't found the target, so it should be false. But if index, like int is like so int initially is the last, like the position of the last element in the list. Remember, we have to start from the end of the list back to the beginning, because when we traverse down, we traverse in the reverse order reconstructed path. The path we constructed is left, left, right, but we have to do it right, left, left to go down. So initially, index is set at the end of the list. Then, but like if index is smaller than 0, it means that we have gone through the whole path, and we can still keep going. It means like the target has to be at this node, so we return true. And then like so if L.getInt, so if like this value is 0, so if at this position the value in the list is 0, it means we go left. So we subtract 1 from the index, right? We go to the previous element in the path. Then we call like recursively call FL int and R.left because we're going left. The same thing. If it is a 1, remember this, if it is a 1, it means we're going right. So we call this recursively on R.right. Yep. So that's basically it. Oopsie. Sorry. I was trying to see the runtime. Come on. Oh, okay, it's pretty good. 32%. It's not what I was wishing, but sure. The third problem, like it only had like 50% pass rate. Not too sure about that, but it should be pretty simple. So it's another, like last problem we tried the reverse thinking thing. This problem is another reverse thinking thing. You just have to practice to think reversely, like. like if you try to do that on every problem, I bet you like some of the problem will be easily solved. And okay, so this problem has given an array nums of integers. You need to find the maximum possible sum of elements in the array that the possible sum of elements of the array such that it's divisible by 3. So we want to find like the largest sum that can be formed by the elements in the array that is also divisible by 3. So in this case, we can pick 3, 6, 1, 8. They add up to 18. And it's the largest possible number that's divisible by 3. That is also the sum of some elements in the array. And see if we have a 4 here, we cannot form anything that's divisible by 3. So we just return 0. And in this case, like we can pick 1, 3, 4, 4. They add up to 12, which is the largest like divisible by 3 sum we can find. So people might be thinking like, okay, I need to find all the combinations of numbers that add up to 3's, like that add up to a value that's divisible by 3. We need to find all the combinations. Actually, no. We only need to find like a few elements. Let me show you how. Basically, first you sum all the elements, right? So in this case, it should be 9 plus 5, 14, plus 1, 15, plus 8, 23. So the total sum of this array is 23. Think about this. If 23 is not divisible by 3, so you have to like, so you have to subtract something from 23, because like you can only form this sum with some elements in the array. So you have to take something out. You have to not include something to make the rest of the sum divisible by 3. So first you try, okay, so what's the largest sum? What's the largest number that's divisible by 3 and is also smaller than 23? It's 21, right? So potentially we want to subtract 2 from the sum. So we want to get rid of a number or like 2 numbers that add up to 2. But instead we don't have 2 in this scenario. So we cannot make 21. So the next smaller number that's divisible by 3 is 18. And we want to subtract 5 from 23 to get 18. And here we have a 5. So the largest sum that is divisible by 3 is 18. And the same goes here. They add up to 14. And the largest number divisible by 3 that is smaller than 14 is 12. So we need to subtract 2 from 14 to get 12. And luckily we have a 2 here. So we're good. And here's a pattern we observe. Say if there's a, so here's how we judge what we should take out. If we have, so for example, if we have, let's see this example. 23, they add up to 23, right? 23% marked 3, so 23 divided by 3 is remainder is 2. So we want to potentially find like either a number that has remainder 2 when divided by 3, like 5 or 8, or we have to find like 2 numbers that's divisible, that has remainder 1 after we after dividing by 3. So yeah, basically like if we're on 23, we want either, so for example, we want to either say we want 1 and 1, which are 2 numbers that has remainder 1 when divided by 3, and they add up to 2, which has remainder 2. Or we just want to find one number that is divisible by 2. And we want those sum to be as small as possible, right? See, like in this case, if we want to choose a number that has remainder 2 when divided by 3, we have 5 and 8, right? But we want to get rid of the smallest one so that we can, like the remaining elements can have the largest sum. So we give up 5. So as you understand the thinking process here, This is basically what I just did. So I said total is like the total is like the total sum of the array. So 23 in this case. Length, the array length. Max is like the max element in the array. And I established a hash map that tells me how many times a certain number appear. So for this array, you have map entries of 1, 1. So 1 appeared once, 2, 1. So 2 appeared once, 3, 1, and 4, 2. So 4 appeared twice. So that's basically what I want to establish in the for loop. And here's just like basic implementation and like adding elements to toad, map, and max, basic operation. And I set the start to 0. So first, if the total sum is divisible by 3, great. We don't need to subtract anything. Like we already have a number that's divisible by 3, and it's the largest possible because it used all the elements in the array. So we just return total. And if the total is divisible by, after divided by 3 has a remainder of 1, I set st to 1. So like st is basically like the value I want to select. That like the potential value I want to select, subtracting from the total sum of the array. So the smallest the smallest number I need to subtract is 1, right? Because the total sum has remainder 1 when divided by 3. So I have to at least subtract 1. And if the total sum, it has remainder of 2 in this case, I have to at least subtract 2 from the total array to get some value that's divisible by 3. So I start from 2. And f, I'll talk about it later. So yeah. Like f is like the first option. So the first option is always like just choosing one value. So if like the remainder is 1, just choose the smallest value that's divisible, that has remainder 1 after divided by 3. So yeah, this is the first option. I just do a for loop. So I start from st and I end at max. So max is like the max value in the array because it cannot be any, like the value in the array, like each value in the array has to be smaller or equal to the max value in the array, right? And then each step I take 3 because I want it to be always has the same remainder after divided by 3. So each time I add I by 3. So if map contains the key of I, so there are recorded appearances of I, then I just set f equals to I and then break. So I'm done. I want to find the smallest value, and here it is. The second option is like I choose two numbers that have different remainder when divided by 3. So if I have a remainder, I want to find values that add up to a remainder of 1. I want to choose 2 numbers that have remainder 2, because like after you add their remainder up, it becomes 4, and 4 divided by 3 has a remainder of 1. So that's also an option that we can choose. So basically, count is like the number of the number of elements that satisfy the conditions. So I start from 3 minus st, right? So if st is 1, we want to find 2 numbers that have a remainder of 2. So 3 minus 1 is 2. That's the remainder we want to get. Same here. If st is 2, we want to find 2 elements with remainder 1. So it's 3 minus 2, which is 1. So the same thing, I increment them by 3 each time. So first, if I hit like a number satisfying the prerequisite, if map contains key I, if count equals to 1, so like count equals to 1 basically means like if previously there is already a number hit, I just make count equals to 2 and s plus equals to I. So now my count is 2. I have 2 of those satisfying numbers, and s I add I to S, like the current value. And also if count equals to 0, so if map.get I is larger than 1, which means that this number appeared twice, and count equals 0, which means like we have not previously met any smaller satisfying numbers. So we just set S equals to 2 times I, count equals to 2 and break, because we want the smallest combination, right? We already have 2 of the same value, so we just get the 2 because they're the smallest. Else, I just like add, so if there's only one appearance of this number, I just add I to S, and then I add 1 to count, means I only got one satisfying number. If count, and eventually if count equals to 2, which means we have already got all the numbers we wanted, I just break it. And then like if count is still smaller than 2, which means there are no 2 elements that satisfy like the remainder here. So the only valid choice is choosing F, like choosing one number of the original remainder. So just subtract F from the total sum, right? Or else I see which option, we have 2 options, we see which option has a smaller value, so that we can make the total minus the smaller value bigger. Yeah. Huh. Seems like it's not submitting. Okay. Well, let me tell you so. Okay. Story time ended. Fuck. Yay. I suck. Okay. Okay. Last problem. I spent 1 hour and 30 minutes on it. And I want to tell you the story about how I solved it. So basically it's saying like you have this map, or like you have this puzzle, this maze, let's call it a maze. The maze is a grid. It has m rows and columns. And like it's represented by like a 2D array. So all the walls are represented by like this mark. All the valid positions are represented by dot. T means the target we want to reach. B means where the box is at. S means where the person is at. So basically like we can push the box however we want. And then we want to find the smallest number of pushes that we need to make the box to the target. Pretty straightforward, right? So in this case, we have to push it to the left. For once, that's one push. Then we push it here. So we push it to the left, another unit, which is 2 push. Then I go around here and then push up, 3 push. Nice, I reached my target. Great. But there are some cases that I cannot reach my target. So here's the thing. So in this case, I start here. So I go up, push the box. The box is here, push the box. But see, the box is here. I'm currently here. But in order to push it to the target, I have to be here to push it up, right? Be here. But I cannot go there because it's like a wall. So there's no way of reaching the target. So the step is -1. Pretty depressing, huh? So here's how this problem differs from a common DFS or BFS problem, is that we have to, for each like push to be valid, we have to check like it's whether I can reach the opposite position of the move. So if I want to move it up, I have to check if I can be down here to move it up, right? So that's what I initially came up with when I first like approached the problem. Okay, then later I got more troubles. Like I got different, like I got new problems after I've gone for a while, and yeah, it was pretty weird. Like when I thought I got it, I saw like 2 more test cases. Like I saw 2 test cases that I didn't pass. It took me 30 minutes to fix the fix the first test case logically, took me another 30 minutes to fix the next test case. Like with 2 more test cases to go, it just seems like so close. But there are like those 2 test cases are logically more complicated than the first 16, which is really depressing. So let me show you. I want to tell you, just like show you the story, walk you through like how I solved it. So basically, like initially I came up with so initially I wanted to separate the problem into 2 steps, right? Because sometimes, because in some cases, like here, I cannot even go to box or T, box or target, right? Because I'm surrounded by walls. So I want to write 2 functions. First, I want to write if I can reach box and target. And if I can, then I check how many steps it takes for me to push box to the target, or if I can push it to the target at all. So first I need to make sure that I'm not surrounded by walls or something, and I can reach those 2, which I use the DFS function to solve, the reachability. And then I use the Bfs function to solve how many steps, what's the minimum number of pushes I can make to push B to target. So 2 functions. And yeah. So basically those are global variables I established. I'll talk to you about this later. So let's first look at this. Yeah, actually let's look at it later. It's just like it's just a simple object that stores 4 variables within it, A, B, C, and D. And it's actually, like later you'll find out it's the location of two like elements. So you see like on a 2-dimensional grid, 2 numbers represents a position, right? So this is position 1, this is position 2. And these are print functions. I just use them to print out the board. Yeah. So initially, I initialized like those 6 variables. BI, represents the location of box. SISJ represents location of the person. TITJ represents the location of the target. And I established a list, but I'll not use it. I didn't use it later. So time reach target. So basically, like for my first DFS, I want to see if I can reach B and T, right? So time reach target is like representing. It's used to represent. If I reach B, I add 1 to the variable, and I reach T, I add 1 again to the variable. And initially, I add 1 to the variable because I have an S. It means like a special, like basically, I think this variable is just recording like how many times I have reached a special character. So S, I add 1 to it, and if I could reach B, if in my DFS I find B, means I could reach it. So I add 1 to the variable. If I could reach T, I add 1 again to the variable. So eventually, like if I can reach B and T, the variable should be 3, right? Because I have 3 special characters in total. It's a global variable too. I put it here. Yeah. So basic stuff. Row and column are also global variables. It just represents like the dimension of the grid. And visited check. So this visited array is for the first. So it's for the DFS. It's what we're doing right now. It's for the DFS. Those 2 are for the BFS. Okay. Just remember this is for the DFS. Then like I traverse through like I traverse through the grid, traverse through the maze to find where S, B, and T are. And then like I set the location of BI, like B to the index value. So then I have like so after the for loop, I have the position of B, S, and T stored in these variables, right? And also I fill the steps with integer maximum, but this is for the BFS. We'll talk about it later. So then, apparently, like I do a DFS on the grid. So let's see how the DFS is. So DFS have BI, BJ, SI, SJ, TI, TJ representing the location of the three indices, like the three special characters we want to reach. And IJ are the current location we are on within the DFS. And this is the maze grid. So if the current location is out of bound, and also if it's visited, or like not also, but like or. So if it's out of bound, or if it's already visited in the DFS, or if the grid has a wall here, just return true. Like I've done my DFS here. I don't want to change anything. So if those cases are like not passed, I just like I just said like this location to be visited, right? Because I'm already on this location. I set it to visit it. And I say, okay, if I'm currently on the location of T, I increase one. I increase my global variable by 1. If you reach B, I increase my global variable by 1. So eventually, like they should add up to 3, plus like the previously added time for the S. Because like after we visited T once, it'll be marked visited. So when the DFS reach it again, it will just return true and do nothing to the global variable. So this will just get satisfied once in total in each DFS, this too. So only add 1, it won't add much longer even if the DFS reach back to this element, to this position. And also basically like I established an array dir. So basically I want to do DFS of, so if I have a node here, if I'm here, I want to DFS on all those 4 directions, right? Because there's a possibility that I reach B and T on each of the direction. So I want to do DFS on 4 directions. So like basically I generate 4 locations. So I generate the position of those 4 elements by using this. So initially like on the first iteration, I subtract 1 from I and J is the same. So it's this location. On the next iteration, I go through those 2 elements and I don't change I increase J by 1. So it's here. And then like, again, this one goes here. And the last 2 goes here. So by looping through the array, I can get 4, like the indices of, like the position of the neighbor elements. So back to the DFS. Yeah. So temp I equals to the dir of S, temp J equals to dir of S plus 1, those getting 2 elements, right? So like, and then I just do a DFS on those with the same BST location and updated I and J. So the elements on the 4 directions and return grid. Hopefully like, so like eventually, so for example, if I start here on this example, DFS will go those 2 and keep going. You'll get those 2 right. 2 out of the 4 directions are valid. Then you will go to here. You will just keep going until it reaches like, it traverses through all the elements in this open field. And of course, you will get B and T. So it passes the DFS. But if I'm here, I search through the 4 directions, no way of getting them around because they're walls. So you just remember walls will just return true. So B and T are not found. So it fails. So I call the DFS this is a main running function. So if the global variable is not 3, right? Just return -1, which means because we cannot even reach box or NT, so we cannot like move them to the target. Then it's like time for a Bfs function, which is more complicated. It's fine, I think. Bfs. Okay, you only have 3 inputs, so because we have the like we basically like record the I and j, like the current value we are on, I and j, and also si, sj, so like where the person, so we basically store the value, the position of the box and the current position of the person, and see in which direction we can make a move, right? We just store the position of those two. And it's stored in the queue because BFS, you always use a queue. So we don't need those as input. We just need to get them out from the BNS construct or class object. So we only need to know where the target position is. So target I, target j, which is basically ti and tj. So see, initially I add this to queue. So I add like a initial starting position, right? Initial starting box position, initial starting person position, so that we have some element in the queue. And then I set it as visited. So visited step. Okay, so visited step is actually like, it just records like how many steps, how many pushes we need to reach a certain index. And because the box is initially at BIBJ, we don't need to move it to make it to BIBJ. So it's just set to 0. And then I do a BFS. Then see, like initially, all the steps within the visited step array set to integer.max value means like initially, like before we do the BFS, all elements are not reached. Like none of them are reached. None of them are reached. So I can print it out for you guys. BFS. It's taking forever. See? So this test case is for this one, for the initial one. So we go here, push it once, push it twice, push it 3 times, right? And then see, like it's 3 on the target. This is the location of the target. So it returns like, see, actually, like, let me print out the grid for you guys too, so you can see it. Like, see, like B at the position of B, it should have been 0, but it just changed to 2, and I'm not too worried about it because like it's the only element that gets wrong, and B cannot be T, so it won't affect my results at all. So I just go here. See, if I push it B once, it goes here. So this is 1 here. Push it B twice, goes here. Push it B 3 times, goes to target. So that's what our B, like this is the visited steps. So apparently, like if the step is larger, if the step has, if the step at a position, the value at a position is integer.max value, then it means like we have not reached it, right? We cannot reach it. So we just return -1 if we reach like an integer.max value. Okay, so for the BFS function, so basically standard way, while Q is not empty, size equals to Q.size and get the BNS, so like BNS indices, pairs, we get them like for size times, right? It's just like a layer by layer thing. So for example, in each iteration, this is the location pairs. And I set the ij to like so A and B stores the location of the B. So I and J represents the location of the B, the box. And SISJ storing the second pair. So this represents where I am at, where the person is at. So this is really tricky. I'll talk about it later. This is super tricky. If I visited, so visited time is like how many times I've reached this element. You might be thinking that, well, actually, let me get a good test case for you guys. Okay, this is a great test case. It's exactly like this is a test case I didn't pass. I'll show you. Show you. You might think like we only need to, so for each location, we only need B to be on it once to reach the target. If we are on it twice, that means we have done something wrong. But instead, that's not the case. Sometimes we have to make B land on a certain location twice or 3 times to be able to go to T. So in this case, think about it. So what you want to do is you want to push it through here, right? You have to go to T. So you go here, push it down, push the box down here. So the box is down here. Then you go back, push it to the left, right? Now the box is here. Then you push it here, right? Now you're on here, right? Because like when the box is here, you're on here, so you push it here. Now S is here, box is here. Now you have no way else, no other way to push it. So you have to push it to the left again, right? Because you're here. So you push it to the left. Then there's a miracle, like there's a strange thing. You go down here, push the box back to this position again. Now you have visited, the box has visited this node 2 times, which is strange. But then you see you can have a way of pushing it up to the target, right? The reason is when the box is here, you cannot push it up because you're here. The only thing you can do is push it to the left. But then you have space to move around. The person has space to move around. And then you push it back and goes here to push it up. Really strange, right? I was like totally confused when I saw this scenario. You can land on a location twice. The visited list is useless. But luckily I found like a way through it. And I found like let's see if this actually accepts. Okay. So I have found that at most, you go to, wait, it should actually be 3, right? Yeah. Oh yeah, sorry. Like, I think you at most land on a location 3 times. So that's why it's like it's larger than 2 to be able to push it somewhere. So the thing is, let me draw a diagram. Or like, let me not draw a diagram. Wait, let me see my time complexity. I'm sorry, guys. Just want to check it out real quick. What the heck? Oh, this is pretty fast, 51%. Okay. Let me actually not. Okay. So in this case, so let's focus on this element, okay? You're here, you push it to the left. And then basically there's, when you go back, so if you ever need to push it back, you don't need to push it here, right? Because B is already on here. By being on here, it only goes backwards, which is useless. It just goes back inside here, right? So if B, so for example, this is where initially we push B to, then we push it here, push it to the left, right? Initially we do that. So if this path doesn't work, doesn't go to T, then there's useless to push it back to here, to push it to beyond here and push it back to here, right? We already failed this location. So when we first visited it, we already failed this. And if this doesn't work, we failed this. This is just like the, it doesn't work if we push it here. If we push it here, then we fail the second direction we can possibly have, right? We only have, when the box is at this position, we can have at most like 4 directions we can go: up, down, left, or right, right? And in this case, the right has already failed because we have already been on it before. Pushing it back is useless. We are just going backward. And the left also failed because apparently T is not on left. So with the first visit, 2 directions already fail. And then you go here, the person goes here, and then you push it back, right? Then there are like 2 more choices. So if you push it up, it doesn't work. You have to push it down. So there are 2 more options. So that adds to at most 2 more traversals to this point. So this point has to be traversed at most 3 times. And after it gets 3 times, continue. So we don't do calculation anymore. It's like basically like it's a full BFS. Like if the 4 directions are possible to go to, I just do a BFS on those 4 directions. So I really want to try to keep the maximum number of times I can visit a node down. I really want to keep that number down because that means how many iterations I've got to go and how like space or time consuming my algorithm is. And luckily I found out like a node can be at most traversed 3 times if there's a valid path. So let's see a case. Let's think about a case. Yeah. And apparently, like if you argue like, okay, I'm here, then I push it to the left, then there's a potential I need to push it here. But when I'm here, I do a BFS, I reach here again. So I would like add an additional 1 when I put it here, right? But so like it will exceed the 3 times I traverse this because I go there and when I go there, go back, it adds another 1. So it adds a total of 2 with going back and forth. But the thing is like, if you can get it back, right? If you can get it back at this position, why would you go there and then get it back, right? It's useless. So basically you just choose the most convenient way. Okay, say if I can go back, I go back. And before like this thing goes back, you already have chosen a direction, right? It's strange, I know it's strange. Okay. Okay, you get the index of like the location of box and person at this iteration of the BFS. Then basically you visited this this location 1 time extra, so you add 1 to the visited times. It's also an array that stores how many times you visited each node or each location. And res is basically like a global variable that stores like which step we are on in the BFS. Because in each iteration of the while loop, we take one more step, and it lists all the possibility we can reach, all the possible locations we can reach on that step. Yeah. So sure, I put that to rest. So that I know how many steps it took me to reach this index. Like here, right? Like here, 3 steps. Then for those 4 directions again, if I establish like the index of the next element we want to reach, and if like the location is out of bound or it's a wall, then just continue. We don't add that to the queue because we don't want to do BFS on those meaningless stuff, out of bound or like a wall. We don't work on that. And T reverse J means like the position the person needs to be at to push the box to TI and TJ. So for example, if the box needs to be pushed down, the person needs to be 1 block above the box to push it down. So it's reverse. See, it goes, box goes here, but person should be here. It's reverse direction of B. So basically minus D1 minus D2 from the original box location. And if it's out of bound, or if it's a wall, and reachable is another like helper function I wrote. It basically means like if at the current location of the person cannot reach TR, like the location marked by TRI, TIJ. So like say if I cannot reach here, I cannot push it down, right? So if it's not reachable, then just continue, does nothing. Or if it is reachable and it's not a wall, I can stand on it. Then I set S temp I to I, S temp J to J. So like it's basically like so after I push the box, I'm on the location of the original box, right? The box is here, I'm here. So this S temp I, S temp J is for the next iteration. So after I push it in whatever direction, I always end. So if I push it here, push it up, I land on the original position of B. If I push it down, I also land on the original position of B. So the SI and SJ for the next iteration, the next point, the next like pair in the queue should always be the original location of the box. So then if all those are satisfied, means B can be pushed. Then like the location of B and location of S becomes the valid location to be added to the next step in the queue, right? Because we can push it down, so it should be the next step. Then, so they should be the location after the next step. And eventually, if I, so like the next step value equals to target I, or the next step value and the next step J equals to target J, means like the location is on the location of the target, which means that we can, after this step, we can push the box to the target. Then add 1 step, right? We can push it to the target on the next step. And set this visited target I, target J to rest. So like how many steps it takes to go to that position and then return rest. Basically, it's like this. And eventually, after the while loop, we've traversed every position and we still cannot reach the target. We still cannot push the box to the target. Then we just return -1. It's impossible. So basically, we can just quickly look through the reachable function. So for each, it's kind of complicated. Like for each computation of reachable, I have to establish like a new visited Boolean and do a DFS. So REA is also DFS, and see if like S can reach like the current position I'm on. If I can reach the target location I want to get, I want to walk to with the current position I'm on. So if I can reach SI, SJ to target I, target J, but those two target I, target J are not like the position of the T. It's just like the location I want to get. See, target I, target J in this case would just be this position. So I'm just calculating whether I can go from S to this position and then push the box in order to push the box down. So I always need a new visited array for DFS. And time before I use this global variable again, okay? Time before, so I want to keep searching special characters. So this case, a special character would actually be this, not so special character, but this is the target I want to reach. So in my DFS, if I can reach this target, I just add one. Yeah, I just add one to the, I just add one to the global variable and it will show up. So if after the DFS, global variable is like increased by one, so if now it's larger than before, return true. If it's not, which means we have not reached the location we want to get to, then return false. And wait. So yeah, basically like I cannot go through B, right? B is a box. I cannot go on it. So I first change the location of B to a wall because it's like a wall. I cannot stand on a box. And then after I do the DFS, I just change it back to dot, like a valid position we can go to. So this is REA is just like a regular DFS. So if SI is out of bound, like the location of S is out of bound, means we cannot walk on it, or if it's already visited, or if it's a wall, just like return true means we do nothing. And then we set like the current location to be visited. And if it's on the target, add one to the global variable, return true. Or else like we do DFS on 4 directions. Pretty straightforward. DFS is simple. Yeah. So basically that's how I solved it. Whew. So thank you guys for watching. I know the last question is a really long one, but hey, like I struggled an hour and 30 minutes on it. Like after I finished it, it was like 300 lines. Then I realized like, then I tried to optimize the code and reduce it to 170 lines. So like I had much more to work on than I currently have when I was working on the problem. So it was a really struggling experience. And I'm glad I figured it out because 8, the question we scored 8 was really challenging for me. And I'm glad I did it. So yeah, hope you guys enjoyed it and actually understand the questions. And if you don't understand it, I hope you understand like the basic idea behind the question so that you can try it yourself. Okay, thank you guys for watching and have a good day.